Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Asad Abbas. This lecture is divided in two parts. In part 1, we will discuss prescriptive process models and uh, the classes, whereas in part 2, we will see engineering process models and types of the engineering process models. Well, here we will discuss the prescriptive process models in terms of improving the software development processes of an organization. So for that, we first need to understand the difference between the prescriptive and descriptive process models. Prescriptive process models tell us how something should be done, whereas a descriptive process model describes how something is done in reality. A descriptive process model is created by observing the process that is actually being performed in the organization, while a prescriptive process model typically aims at addressing all the relevant issues of developing a piece of software. So, a descriptive process model describes what people do every day, which means that these models they actually reflect the current practices of organizations, whereas a prescriptive model tells people to do something differently, which means that they need to change their behavior. Actually, getting people to change their behavior is one of the most difficult tasks in software engineering. So, the successful deployment of a prescriptive process model is difficult indeed. Here you can see in this figure that there is a loop between the prescriptive and descriptive models, which means that in order for an organization to improve its current practices, it needs to deploy the prescriptive process models, or it should follow the guidelines of these models. So this process is in fact a continuous improvement process where organizations continuously keep on improving their processes by following the guidelines. The prescriptive models are categorized into mainly two categories, that is life cycle models and engineering models. The life cycle models include models such as waterfall, iterative enhancement model, prototyping model, spiral model, unified process, IBM Cleanroom process, and incremental commitment spiral model. Whereas engineering models include process model for statistical testing, process model for hybrid cost estimation, and extreme programming process model. So in this video, we will discuss life cycle models, whereas the engineering models, they will be discussed in the second video of this lecture. So here we start our discussion on life cycle process models. Life cycle process models actually cover the complete life cycle of a software product, or a large fraction of it. That is, the activities specified in these models continue throughout the life of the software system. These process models typically tell the software engineers what to do and in what sequence to do, but not how to do it. Moreover, these models do not recommend or prescribe any specific method or technique, but they rather demand that something needs to be done effectively, meaning that whatever method is applied, it must yield the expected results. For example, a life cycle process model may demand that traceability be established between requirements and components, but it will not prescribe how this should be achieved. So this must be determined by the process engineers at the respective organizations. We have already discussed waterfall model, iterative enhancement, or incremental model, prototyping, spiral model. So we will not discuss them again here. In this video, we will only discuss the incremental commitment, spiral model, unified process, and IBM cleanroom process. Well, the first life cycle model that we discuss here is Incremental Commitment Spiral Model, ICSM. Boehm proposed the Incremental Commitment Model, ICM, as a life cycle model for developing large systems with high development risks. And typically, these systems were developed for military organizations. In subsequent years, the model was refined into incremental commitment spiral model, which is also called as ICSM. Similar to the original spiral model, it considers a spiral covering the development life cycle of a system. However, a difference is that it makes the risk-driven decisions explicit, they're highlighted by the stakeholders, commitment reviews, which are in fact 6 reviews, and it has 4 possible exits. So a key aspect of this model is that it requires the stakeholders to perform the feasibility analysis at each stage to determine whether to proceed with the project activities or not. Moreover, the exit strategy that I mentioned before in the ICSM, it offers the stakeholders to stop a project or re-strategize to mitigate the risks before wasting lots of resources. Here we can see that there are 6 risk-based stakeholder commitment review points. For example, exploration commitment review, valuation commitment review, foundations commitment review, so on. At each of these review points, the commitments to invest the resources are reviewed, and these review points highlight the opportunities to proceed or to skip the phases or backtrack or terminate the project activities. In the exploration phase, which is the first phase here, the development team focuses on initial scoping, studying the current systems, and exploring the alternatives. Similarly, the activities in the valuation phase include developing operational concepts, prioritizing the requirements, assessing the non-developmental products, and studying the business case analysis. Then, in the foundation phase, the development team focuses on building the system and software architecture. Similarly, it focuses on acquiring the non-development items and creating a development iteration plan. Uh, also, there exist one or more development increments in the development phase. Additionally, our transition plan is also defined in the development phase. Finally, the project is delivered and deployed, and hence it comes into the operations phase. In addition to the commitment reviews, the ICSM has 4 exit strategies which suggest different alternatives when the risks are, for example, as you can see here in the figure, when the risks are acceptable. Similarly, the risks they are high, but they can be addressed. The risks can be too high, which cannot be addressed, or they can be negligible. Here we will discuss each of these risks and exit strategies. So the first one, if the identified risks are acceptable for the stakeholders and well covered by the appropriate mitigation plans, then the project will continue into the next spiral. An example would be a software system that does not reach its intended throughput, but that scales well with the number of CPUs. So the mitigation plan would be to add additional CPUs in order to reach the target throughput. So here is what is determined to the exit strategy. Similarly, the second one, if the identified risks are high but expected to be addressable, the project will remain in the current spiral until those risks are resolved or covered by the appropriate mitigation plans. An example would be like working out safety cases for a safety critical system or producing acceptable versions of the missing risk mitigation plans. Similarly, if the identified risks are negligible, the project can skip the next spiral. This means, for example, that if the risks are determined to be negligible during the exploration spiral, both the valuation and foundation spirals can be skipped in this case, and the project can go directly to the development spiral. For example, this can happen if the exploration spiral finds that the solution can be easily produced by tailoring a commercial off-the-shelf package rather than developing a custom system. So in that case, the subsequent spirals might be skipped. Similarly, if the identified risks are determined to be too high or they cannot be addressed, the project should be terminated or rescoped. For example, sometimes it is determined that the market window for the product under the development has already closed. Hence, the project should either be terminated or it should be rescoped to address a different market sector whose market window is still open. It is important to mention that a necessary precondition for applying the incremental commitment spiral model is the understanding among all the involved partners and their willingness to stop a project if the risk analysis suggests something like this. In other words, the incremental commitment spiral model cannot be applied to the projects that must deliver a result in any case, no matter how good or bad it is. So, applying the incremental commitment spiral model also requires the capability on part of organization to identify and assess the risks. So the advantages of incremental commitment spiral model are the first one is that the incremental commitment spiral model prevents premature or total commitments, which can lead to a situation where there is a no way back. The early identification of project risks and either their mitigation or the adjustment of the project scope facilitate the estimation of expected and actual project results. Additionally, the ICSM opens an exit strategy to stop a project before burning away lots of money without the need for anyone to lose their face, which can be very beneficial in projects where organizational politics plays an important role. The second model we discuss here is unified process. The unified process is a generic process framework for software development, and it was published by Jacobson, Booth, and Rumbaugh in 1999. It consists of a generic description of phases and activities that can be adapted for different types of organizations and for different application domains and for different project sizes. The unified process distinguishes project phases like the waterfall model does and supports iterative development within the phases like the iterative enhancement model does. It also specifically considers risks during the iterations. So it has some features of spiral model. In addition, it contains traces of the prototyping model since it recommends uh, building the prototypes within the iterations under special circumstances. The unified model has phases such as inception phase, elaboration phase, construction phase, and transition phase. The inception phase of the unified process encompasses both user communication and planning activities. By collaborating with the customer and end users, business requirements for the software are identified and a rough architecture for the system is proposed. And also a plan for the iterative and incremental nature of the resulting project is developed here. Then elaboration phase refines and expands the preliminary use cases that were developed as part of the inception phase and expands the architectural representation to include five different views of the software. So these views include the use case model, the analysis model, the design model, the implementation model, and the deployment model. Then the construction phase of the unified process is identical to the construction activities defined for the generic software processes. The transition phase of the unified encompasses the later stages of the generic construction activity and the first part of the generic deployment activity actually. So then the software is given to and users for beta testing and user feedback reports both defects and necessary changes. At the conclusion of the transition phase, the software increments they become actually a usable software release. The unified process is a popular lifecycle model. However, there are certain challenges that are related to it. For example, its application requires more process maturity, like that experience and skills are needed to clearly distinguish the project phases and the development activities. Similarly, it must be adapted to the respective context, a fact which is often neglected. Then the iterative nature within the phases may be confusing because the phases make the unified process look like a waterfall model. Overall, the unified process is a comprehensive development process that must be to the specific adapted to the specific organization's needs before it can be applied. Then the next life cycle model we discuss here is Cleanroom development uh, process. This was published by Mills, Dyer, and Linger in 1987, and the process distinguishes itself from other approaches by focusing on the formal verification of correctness as opposed to trying to eliminate as many defects as possible by applying some testing technique on the system. The clean room development process is based on developing and or certifying a sequence of software increments that together form the final system. So each increment is developed and certified by a small independent team. The development team assures correctness via a formal specification, design, and verification. In fact, team correctness verification takes the place of testing and debugging. The clean room development process is therefore considered an iterative process which works like an iterative enhancement model. The clean room development process is depicted in this figure. It has two cooperating teams, that is the development team and the specification team. Initially, both teams together analyze and clarify the customer requirements. If requirements are unclear, the teams can develop prototypes to elicit uh, uh, the feedback iteratively. During the specification activity, the teams produce a functional specification and a usage specification. The functional specification defines the required external system behavior in all circumstances of use in a formal way, whereas the usage specification defines usage scenarios and their probabilities for all the possible system usages. After that, incremental development starts. For each increment, the development team creates a system design and carries out correctness verification for the respective design. Then, using the usage specification, test cases are generated that reflect the expected use of the accumulated increments. Each completed increment is integrated with the system, that is all the prior developed increments, and delivered to the statistical test team. The previously created test cases are then run against the system, and the results are checked for correctness against the functional specification. The elapsed time between failures is measured and passed to a quality certification model which computes the objective statistical measures of quality, such as mean time to failure, etc. So all the errors found during testing are returned to the development team for correction. The cleanroom development process has proven to be able to produce high quality software. However, it is not widely adopted, and the possible reason might be that in order to correctly develop a software system with Cleanroom, all involved developers and development team members must be highly skilled, especially with respect to the formal specification and verification. Considering the context in which software is being developed today, this prerequisite can only be met under very rare circumstances. So that's one of the major reasons of the that hinders the adoption of this model. So that's all about our discussion on life cycle models. In the next video of this lecture, we will discuss the engineering models. The materials in this video are based on the book titled Software Process Definition and Management. For more details, you can consult the book. Thank you.